Right, this is the fourth application problem for integrating exponential functions, and it's a really good question. It's one that I've seen pop up on the HSC, and a concept and understanding that's really important, I think, for you to learn, because you can apply it to a number of different areas. Firstly, this is not a typo. You'll have spotted that straight away, that it's talking about y equals log of x and what that looks like. Well, on the face of it, it looks quite strange. It's one of those questions that you really got to get into and kind of peel back some of the layers on to get a full understanding of what it's asking for, and then look at how you can apply applications to this particular question. Now, with anything that we've been talking about today, we've spoken a lot about sketches, so we're just going to do a quick sketch here, like this, not the straightest of lines. A rubber seal has a shape generated by rotating the region under y equals log x between x equals 1 and x equals 2. In fact, I better just put that in there. The function y equals log of x has a graph that looks something like that between 1 and 2. So we're looking at this region here. Now, the issue we've got here is that this is being rotated about the y-axis. Okay, so it's been rotated that way. Now, the problem with this, though, is that it's asking for the region under the curve between x equals 1 and x equals 2. So it is the area that we've shaded in, but it's rotated around the y-axis. You remember that when we met the topic of volume and the volume around the y-axis, what we have to take into consideration is when we're calculating the volume between the curve and the y-axis, and it's rotated around the y-axis, the region that it takes into consideration is the region between the curve and the y-axis, not the region between the curve and the x-axis. So we can't actually, the problem is we can't do what it's asking at this moment in time. We can't actually rotate that area around the y-axis. So we've got to come up with an alternative approach to this, and this is where the code comes in. What you've got to think about is if this is actually rotated around the y-axis, what you'd end up with is, if I was to draw a mirror image on here, like so, sorry, not like that. It would look like that there, and then that's rotated around, and see, that would come around like so. And would give us that volume. Now, we can't do that. We can only, if we're rotating around the y-axis, we need to have a region between the curve and the y-axis. So we need to come up with an alternative way of solving this. So what we're actually going to do here is, if we focus in on this part here, and look at this region. Now, let's say that together we combined this entire piece, so this rectangle, and rotated that around the y-axis. Well, if we did that, what we'd do is we'd end up with a cylinder. It would be rotated around the y-axis, and it would look something like that. And then to put that into context of where that would fit on the graph, that's the y-axis right there. If we're to look at dimensions of this, if there's the centre, there would be the centre, that would be the radius would be 2, and then we'd have the height of it. Now, so what we're actually going to look at here is we're going to look at, and this is the complicated part of this, we're going to look at some compound volume, because what we're going to look at is we're going to take the green region we've got here and rotate that around the y-axis. And then if we subtract that away from the cylinder, it will actually give us the volume of the grey bit as if that was rotated around. And this is the confusing part of this question. So what we're actually going to do here is we're going to take the volume of the cylinder, and if we look at the formula for the volume of the cylinder here, the one value that we really need is we need the height. We need this value here. Well, that's just the y-coordinate when x equals 2. So given that this is the function y equals ln x, that means this value here is ln 2. So therefore we know the height from there to there is ln 2. we know that the volume of the cylinder is pi r squared h. So the volume here is equal to pi times the radius squared times 4 times h, which is ln2. And we can write this then as 4 pi ln2. Okay. Is our volume of the cylinder. Now we need to work out the volume of the green section that's being rotated around. So we'll call this V1 for volume. Now, to get the volume, we need to know what the curve is, the equation of the curve is in terms of y. So just to recap in terms of volume around, if we just write this down, volume around the y-axis, volume equals pi times the integral between a and b of x squared dy. So we need to rearrange our expression. So at the minute we have y equals, where's that function got? ln x. Rewriting this gives us x equals base e to the power of y. So you can see now where the exponential part is coming into this, so we get x squared. Now if we square this, because we need the x squared component in our integral, we get x squared equals, and we square e to y, we get e to the 2y. So therefore, the volume of the green section is equal to the integral, and we need our bounds, so from a through to b, so it's the integral from 0 up to ln2 of e to the 2y dy. And then if we go through and we integrate this, we get equals e to the 2y, right? So the power of that is 2y. Differentiate that, we get 2, and we divide through by that, so we get a half e to the 2y between ln2 and 0. So we go through and evaluate that, we get e to the 2 ln2 on 2 minus half up to e to the 0. Now we can do quite a bit of simplification here. I'm just going to write this out just to help you out. Is e, this becomes e8. Now, using the log law we had before, if we've got a value at the front here of a log like we do, we can take that up and write it there as a power instead, and we get 2 squared, which gives us ln4 all over 2, minus e to the 0 is just 1, so that becomes minus a half. Now, I'm just going to have to take this over and use this space here. Now, e to the ln of 4, e to the ln 4 is actually just 4, so that becomes 4 over 2, that's a half. So we end up with 4 over 2 minus 1 over 2 is 3 over 2. Okay. Now, just quickly, for those of you wondering, the part where I said e to the power of ln4 equals 4. Just a reminder, this base here is e, and when you've got a base and you raise it to a log of the same base, it equals the value of that log, so that just equals 4. That's where that part comes from. So we get the volume 1 equals 3 on 2, and we can write in there units cubed. And then we can say, well, therefore, the total volume is equal to, as we said, it's the volume of the cylinder, so 4 pi ln2. And notice there's one obvious mistake that we've made all the way through here, and that is the pi out the front, pi out the front, pi, and then therefore in our answer we'll also get, apologies for that, often overlooked. So we'll get the total volume is the area, the volume of the cylinder, so 4 pi ln2 minus the volume of the region between the curve and the y-axis, which is what we just worked out, which is 3 pi on 2. And then from here we can take out pi as a common factor. To simplify this expression here, you can see one of the terms is a fraction, so we'll take out the over 2 part. Now, if we divide through by 2, that actually gives us 8 ln2 minus 3, and that is units cubed. All right, so it's It's a really good question, is that one. Lots of different skills being tested there. Yeah, it's volume under a curve, but it's actually, so the volume around an axis, but it happens to be the y-axis. It's the fact that we can rotate, we can rewrite the log to give us an exponential, and therefore we can use that to then integrate. It's also a nice little lesson around the fact that we can do compound area here, looking at the rectangle and rotating that around gives us a cylinder. So there's a lot going on with that question. It is a quite complicated question, but I urge you to have a read over that. Let me know if you have any difficulties answering that. It's certainly a higher level question within this topic. And remember that volume around the axis is it's now an extension 1 topic. So I'll just put the M and E in, and this one here is now also an extension 1 topic. And now it's been examined at an extension level rather than a 2-unit level. I wouldn't be surprised to see questions like this being thrown in.